Okay, perfect. So, hi everyone, my name is Christian, and we're going to start with the first part of using supercomputers, where I'm going to show you, I'm going to give you an introduction to supercomputers, what are they made of, and a brief introduction on how to use them, how they are shared across researchers, and finally, how to the basic interactions such as submitting programs for execution and understanding how to monitor your jobs and do basic operations such as launching a job, canceling jobs, or writing files and scripts. The only prerequisite knowledge is Linux, because supercomputers run Linux, the operating system Linux. And yes, we are ready to go. And we start with an overview of supercomputers. A supercomputer is an hardware and software infrastructure dedicated to computing. It allows researchers to perform very big calculations. The number one supercomputer by capacity, by compute capacity, is Fugaku. It's shown here as an example. And it is capable of performing 415 petaflops. That is a billions of operations per second. This is several orders of magnitudes more than your laptop. And this is the most powerful supercomputer in the world today. And it allows thousands of researchers to perform their calculations at the same time. Another example of supercomputer is Summit. We are going through some examples just to give you the idea. Summit is a bit less powerful of the first one, but still it's it's the second supercomputer in the world for compute capacity. It's in the USA. More or less every country has, every major country has a supercomputer that is used to boost this, the research and the science, the public research, but also the classified one. This is because in today's world, the science experiments are mostly run on supercomputers through simulations. For Australia, well, we have in Australia we have GADI, which is at the moment the most powerful supercomputer in Australia. It ranks at the position 53 in the top 500 list of most powerful supercomputers. Well, we are going to have here at Pawsey, hopefully very soon, a new supercomputer, which will be more powerful than that. Actually, 50 petaflops of compute power when we'll be ready. But currently we have Magnus. Magnus is a 1 petaflop supercomputer, which has been active for almost 8 years now, my understanding. And so these are just a few of the examples of supercomputers that today are running experiments by thousands of researchers. Today, we are not going to use Magnus. We are going to use smaller clusters that we host at Pawsey. One is Topaz, which is a GPU-focused system. So a system may have CPUs and may also have GPUs. Topaz is a system that, of course, has CPUs, but also provides around 40 GPUs for GPU-accelerated computations. This is an image instead of the first phase of Setonics. So supercomputer is usually delivered in phases due to high complexity. The first phase of Setonics, which will be here, actually is already here, but will be available to researchers next year, will provide 3 times the compute capacity of Magnus. And once completed, it will provide 50 petaflops, as I said, 45 of which comes from GPUs. sounds for who is new to these terms. This all may sound very complicated, but you get the hang of it. So the important thing to understand here is that supercomputers are very powerful, and they are very different from the computers you're using in your everyday life, such as workstations and laptops. The reason is that supercomputers are made to be used by several researchers at the same time, and it has to provide an enormous quantity of compute power. To do so, a supercomputer is made of several, actually many we can say many computers put together. But these computers are not are similar, maybe similar in performance as a workstation, but the architecture is actually very different. A supercomputer has a complex hierarchy. Starting at the bottom, we have the compute plate, which is made of usually on this system, the representative is made of 4 compute nodes, but usually several compute nodes. And the design of these nodes are optimized for taking the least space possible, because these plates are then put together in what we call chassis. Each chassis has around 60, in this case 64 compute nodes, packed together again to minimize the space utilization, but also try to decrease the energy dissipation, and try to, the whole design is focused on packing together in the least space, least amount of space possible, as much as compute power. And then the chassis are put together in what we call cabinets. Each cabinet, we can see, provides already around 400 compute nodes, that is 400 computers. And finally, a whole supercomputer is made of hundreds or even thousands of these chassis, of these cabinets. And the nodes are then connected together through a very powerful networking infrastructure that we call interconnect. So a supercomputer is not a single computer, a very powerful single computer or big computer, but it's many, many computers connected together to provide a huge compute capacity. From the user point of view, a supercomputer can be abstracted in the following way. We have several types of nodes. The first type is the login nodes that we have encountered already. These are computers, let's say, designed specifically to let the users access the system. Then we have the compute nodes where the actual program, the programs of researchers run on. They are the allocation of compute nodes to the various programs is decided by the scheduler. So since we have so many compute nodes, how you decide which one to use and how to know when one is free or not? Well, you don't know that, you don't decide that, but it's a program called scheduler. The scheduler collects your programs and your requirements, and then finds the best time and the best nodes to execute that program for you. We have then the data movers nodes that are specifically designed to, or they have the purpose of moving in and out of the supercomputers a large quantity of data. Data on the supercomputer is stored in high-performance storage. It's high-performance storage provides a very large amount of space where users can write to or read from at a very high data rate. The storage is visible from every node in the system to provide the an easy interface for programs to read from and write to. So as I said, a supercomputer is made of several compute nodes, and that is where the program runs. Each node is characterized by high-end components such as very performant CPUs, very fast memory, and possibly additional hardware such as GPUs. All this hardware in a single node is connected through a very high speed infrastructure, but also compute nodes themselves are connected to each other through the interconnect, which provides a speed around 100 gigabytes per second. This is a picture of the hardware making up the interconnect. It's very messy, so you don't have to deal with that likely. Well, how you are going to use the compute nodes, or better, how they are best used? Well, the reason you can unlock the high compute capacity or compute power of a supercomputer is to run parallel applications or parallel jobs. But there are several ways of making an efficient use of supercomputers. You may have large calculations that cannot be hosted on a single machine because maybe of high memory requirements or would take too long to compute, way more than the machine could possibly handle. So you divide the problem in subproblems and assign to each subproblems to a different machine. That is one way to go. Or you can see you simply want to obtain the results faster, and so again you divide your problems across the compute nodes to obtain a faster executions. And a third way is when you have several computations to perform, several programs to run maybe, and then you may run these programs at the same time on different compute nodes. So there are different ways, different patterns through which a supercomputer can be used. The fast storage, the storage itself actually is does not physically reside in a compute node, but it resides in different cabinets. But the storage itself is connected to compute nodes through the same interconnect. It provides, as I said, a large amount of space for users to read or store large data sets and read to and from at a very high speed, at very high data rates. Because if a program runs very fast on a compute node because it's very powerful, but then it's stuck reading and writing files, then we don't go that far. So we need also a very fast high-performance storage. Compute nodes may also have local storage that is something similar to the storage on your computer, so it's physically attached to the node, but it can be used as a cache or a temporary storage. But the main storage is the main file systems are actually the high-performance ones. This completes the overview, and we are going to now see how you can log in a supercomputer. And we have seen that already, but we're going through again. A login node, you connect to a supercomputer through the login node. The login node must be used to perform administrative work, such as preparing your program for execution, manage your workflows, checking the results, or install software, writing scripts, and etc. But it must not be used to run the programs. I mean, must not be. You can prepare your programs to run, meaning you can write the scripts, and that script can be submitted to a scheduler on the login node, but you cannot execute the program as you would on your workstation. you cannot launch your program directly, because if everyone did so, then the login nodes would be overwhelmed by all the programs running on them. We have just a few login nodes compared to the large amount of compute nodes available. This is an example of terminal where now we have seen how to log in on Zeus or Topaz. You log in through, you don't have obviously a screen on a supercomputer. A supercomputer is a big infrastructure in a very isolated room, so you don't have physical access to the supercomputer. You connect to a supercomputer remotely using your own laptop or workstation and a program that implements the SSH protocol, which can be the SSH command or MobaXterm, for instance. And hopefully you all managed to get on the supercomputer by now. If not, you can write on the chat. Someone will help you. This is the first exercise we have. The exercise will ask you to simply log in on Zeus and see if you can perform these simple operations. When you connect on the supercomputer, you will be shown a prompt. If successful, you will be shown a prompt that will accept commands such as cd, pwd, ls, the normal Linux commands you would execute on your Linux machine if you have Linux. But this is running on the login node. These commands are running on the login node, and they are to be used to prepare your workflow and to submit the jobs to the scheduler. I guess I'll give you a couple of minutes to try again this one. I guess I can do it together with you. I'll share my whole screen because now I'm sharing just the presentation. Oh, I think oh, okay. I think now you can see my terminal, right? Okay. Okay. Better?
Yeah, I use the whole screen if you can.
Oh, the whole screen. Okay, is better.
Yeah.
Okay.
Maybe even a bit bigger.
Okay. So now I'm using my own account, so I don't have it's the same. If you connect on Zeus, then you have a prompt similar to mine. And if I type the command pwd, it shows my home directory. Unless we show the content of my home directory, I have a few files now. And if I type host name, for instance, well, it returns Zeus1. Zeus1 is one of the login nodes. So to show that we are actually on the login node of the supercomputer. Because this exercise is more to verify that you actually can connect. So I'll move on now. And the second exercise is actually to do something a bit more complicated. Well, no, I wouldn't say complicated, but
Christian, just before they git, maybe they need to change to cd to my scratch, just to be sure.
yeah, sure. So the directory were created, right? So you all can cd to my scratch. This is an environment variable which is defined when you log in, and it's just a shortcut to this directory, which brings you to one of the high performance file systems that we have, which is suited to run intense higher computations, even though right now we are not doing so, but it's always a good practice to to write and read your data from the scratch file system. So the thing is that when a supercomputer, as I will explain later, it's used by many researchers at the same time. It means that although the file system is a high performance one, it can be still put under high pressure if many users run intense programs that writes or read a lot of file. And sometimes it becomes slow, or the program can hang. And hopefully it's not too common, but it happens. So this is the kind of problems you may have, and that you usually don't experience on your laptop because it's only you who is using your laptop. But on a supercomputer, you always have to keep in mind that many other people are using it at the same time. And so you can have these kind of issues. But if everyone now manages to use or has managed to move to the directory, we can proceed with the exercise. I can give you a couple of minutes and I will do it together with you. So the exercise, go back on the slide, will ask you to download the Git repository. So it's, for those of you who don't know, Git or this procedure is essentially, it's a website. GitHub is a website where we can store code, public code. So, and with this git command, we are basically copying that code on the supercomputer from this website. The command git clone will download the code essentially. And so if I execute the command, I've linked I posted the link on the chat so that you don't have to type it manually. So as you can see, I've cloned the repository or copying the code, and now I have a directory called introductory supercomputing, which is a directory we use throughout the session to do exercises, execute sample programs. So we can use CD to move into the directory, and we can check the content. We have several folders, one for each exercise.
So if something appears on GitHub, git clone with the site address clones the directories into your current directory?
Yes. By default, if you use the command shown on the slides, I will clone the directory in your current directory. We'll clone the repository in your current directory with the same name of the repository. But you can change that by passing an additional argument, specifying the path or where you would like the directory to be stored, and the repo to be stored. That's from the top of my memory, but you can specify a different folder. Okay. Couple of more seconds, I guess, and then you can try to move on. Okay, so we are at the end of the login slides. The common problems that you may have already encountered is that, for instance, you can your access may be revoked due to many failed login attempts. So if you failed to log in 3 times, three consecutive times, then your internet address is blocked due to security reasons to avoid potential attacker or any kind of disruptions to the system. If you are in that position and you believe that it was an accident, then you can write to our help desk email and ask to be unlocked. Other problems, maybe you forgot your password. Well, not in this case, we are just using test accounts, but when you will have your like real account, you may forget your password, and so we have a service to reset the password. Sometimes the supercomputer is unavailable due to maintenance. We are fixing things or improving stuff, and so we need to take away the access from users so that we can work on it. And so if you realize that you are not able to log in, it's maybe because the system is unreachable for the moment. And you can check when this is the case on this web page. We have a maintenance and incident page where we post or we advertise actually earlier the outage.
That's a really good point, Christian. So you're locked out after 3, potentially 3, because it thinks if you do 3, one right after each other of them, you will be locked out. But also it's good to keep a lookout, because I think it's the first Tuesday of every month there is some maintenance on the systems. So you want to make sure that you keep looking at the maintenance schedule and don't leave anything to the last minute in case there is a maintenance schedule going on for the supercomputers. Pascal?
I was just going to mention that in terms of SSH, it's not that 3, let's say if you put in the password, you'll try to log in, so you put an SSH command once, you have 3 attempts to put in the right password, it then closes the connection. It doesn't fully block you out, it just closes the connection. It's if you do that SSH command many times, always putting in the wrong password, that it'll then start looking at your IP, and it's also usually key to the rate. So obviously for denial of service attacks or other attacks, the reason why some programs like FileZilla, like transfer programs that people might use that have graphical interfaces are a bit dangerous is because they have this automatic retry if there's a failed attempt, and that automatic retry will try continuously super fast. So for us, it looks like someone's trying random passwords or the wrong password over and over again very quickly. That looks like an attack. And so then it definitely gets blacklisted. If you type in your password 3 times and then get the connection closed, and then you type the SSH command again, and you type 3 times, the password gets closed, you type it slowly. I would take a moment and make sure you got the right password. If you do it again, that's when it gets an issue. So it's not just 3 attempts, it's 3 full attempts of SSH with the wrong passwords all the time. That ends up being an issue. Also, the rate is a key thing. So if it sees passwords being put in microseconds apart, right? That's a program, it's a bot just putting in passwords. So then it's going to try to block the IP. So the firewall is a bit intelligent about how it blacklists stuff.
With that, there's just a piece of trivia that's very interesting. Cloud, as soon as you set up a VM, a virtual machine on Pawsey's Nimbus Research Cloud, it's less than a second, and there are bots that are out on the net that are hitting it, trying to get into it. It is less than 1 second, and something recognizes it out there and it's trying to hit it. So security is a real issue and a real consideration, I should say. So that's why when you're using the machines, you want to keep your passwords, not these, obviously these are on training accounts that are very, they're separated from the rest, right? They're protected, that you can't get beyond that. But when you do have your password for your projects, you don't want to be giving that out, and you don't want to be giving your username out. Don't share that. Pawsey staff will never ask you to share that. So if somebody asks you to share that, it's not from us. So just keep that in mind.
So to avoid all these problems, you can set up the SSH key authentication, which it's a safer way to communicate with the supercomputer. You can find a documentation at the link on this page. Essentially, you will create a couple of files. One is the public key and the other is the private key. You will copy your public key file on the supercomputer and use your private key, and the pair private public key will be used by SSH to communicate safely with the supercomputer without you being asked for the password. Obviously, do not share your account. You're not allowed to share your account with other people. It's only to be used by you yourself. And again, do not provide your password to anybody else. You can access the supercomputer we have seen is used through the command line, so there is no graphical interface usually. We have, however, for some applications, you may need to visualize a large amount of data. And we have, for that purpose, we have a visualization nodes. They can be accessed through a graphical interface, but it's only limited to those use cases. So visualizing large amount of data with specific programs and for a specific set of nodes. But usually, if you want a graphical interface on the compute nodes in general, you may need to use the SSH GUI forwarding capability -X if you want to open a program with a graphical interface on the supercomputer, but just for the lightweight ones. Usually, it's not advised for you to run programs with a graphical interface, not on the supercompute nodes, unless in very specific cases, such as debugging. But for the time being, just consider using the supercomputer only with the command line. Now, the second part is sharing supercomputers. As I said, supercomputers are used by many researchers at the same time. This is because the infrastructure is very big and provides an enormous amount of computation, so can be used by many people and should be, because running a supercomputer is very expensive, consumes a very large amount of electricity, and whether it is idle or not, there's still consumption. So the best use of it is to get it at full capacity as much as possible. That means also having jobs running or programs running nights and weekends. And since we want to achieve that objective, and we have many users running many programs with different characteristics. Some users may run very large jobs using a lot of CPUs. Other users need a lot of memory, and etc. We have different usage patterns. Running programs on a supercomputer requires an orchestration. That orchestration is provided by the so-called scheduler. A scheduler is a program, and we are suppose it uses the SLARM scheduler. Is a program that takes the requirements and the program to run from every user, and then decide which program to run at any given time with which priority. From the user side, there is the so-called job preparation. The user selects the program to run and describes the resources needed to do so. Then gives this information to the scheduler through a script that we call batch script or job script. On the scheduler side, we have many scripts or many jobs to be run. So the term job refers to a program together with the requirements needed for it to run. So the scheduler has many jobs to run and has to decide which one to run at any given time. Well, it can run all of them if there is the capacity, but most of the time there are so many jobs that the supercomputer cannot run all of them at the same time. So some jobs need to wait for their spot on the supercomputer. The job of the scheduler is to optimize the usage of the supercomputer, that is fill all the compute nodes, or as much as compute nodes as possible. And at the same time, it needs to provide a fair a fair waiting time to all the users. So a user must not wait 3 months for his job to run. What we have is that from the scheduler perspective, the compute nodes are divided in partitions. This is because we may have some nodes with some characteristics and other nodes with other characteristics. For instance, some nodes may have only CPUs, other nodes may have also GPUs, other nodes also may have a higher quantity or amount of memory available. So based on the compute node characteristics, we have different partitions. But to each partition, we have an associated queue to which users can submit jobs. So if a user has as a program that needs a lot of memory, can submit a job to the high memory queue. Or a job needs GPUs, then the job can be submitted to the GPU queue. So in this picture, it's a rather, at first, messy representation of the utilization of a supercomputer. On the x-axis, we have the start and end times, we can see, or the timeline. And the y-axis, we have the CPU IDs. And each color rectangle is a job which spans a certain timeline, a certain interval in time, and a certain range of CPUs allocated to it. And we can see that the scheduler tries to fill in the gap, every gap in the graph. So we have many jobs running at every point in time. The key point here is that your job may not run instantly like it happens on your computer, but it may most likely waits in the queue for a certain amount of time, can be hours or sometimes even days before it runs. And so you need to automate as much as possible, write your scripts such as that it's ready to execute at any point in time, and then go and do other stuff. You don't have to wait in front of the screen for your job to start. I'm going to introduce now some terminology that is used throughout our documentation. It's common terminology across supercomputing centers. So as I said, a partition is a set of nodes with an associated job queue. Each partition characterized has some characteristics. Some partition may have a longer work time, or allows a program to run for longer times, or gives access to a higher quantity of memory, as I said. A cluster is all the partitions and usually corresponds to a supercomputer. So sometimes you can hear a person calling the supercomputer a cluster, or vice versa. It's basically the same thing. Now, as you can interact with the scheduler with several programs. So I guess if there are any questions, this is a good time to ask, and you can write in the chat and someone will read out loud the questions maybe. But you interact with the scheduler. So the scheduler is a program running on the supercomputer, and you can interact with the scheduler with several commands, several Linux commands. The first one that you're going to see is the sinfo command. The sinfo command is used to explore the characteristics of the cluster at any point in time, or at the time you call the command. You usually use the sinfo command when you are logging on the login node. All these commands must be run on the login node. I mean, can be run on the compute node, but usually you run on the login node. And the sinfo output is shown in this slide. The sinfo shows yes, Pascal?
There's a good question that probably is good to record, which is what's the difference between a partition and a node that you run on? So that just making sure what's clear what is a node and what is a partition.
Yeah, definitely. So a node is actually the physical computer which will run your program, and it's a single entity. It's a computer. A partition instead is a set of nodes, and a partition is somehow an abstract concept. A partition is a concept defined in the SLARM configuration. And a node, several nodes may be part of a partition. So each node, by definition, each node is part of a partition. And a partition, so is a set of nodes with common characteristics. So for instance, there is the partition with high memory, where each node in that partition have a larger quantity of RAM available with respect to other nodes. Other nodes may have GPUs, and so those nodes are collected in a set of all the nodes having a GPU. So if you have a program that needs a GPU, then you don't want to submit that program to a node that doesn't have a GPU. You want a node that has a GPU, and so you're going to submit your job. You're going to tell the scheduler, run this job on one of those nodes that has a GPU. And to do so, you say, queue the job on the queue associated to the nodes having a GPU. So it's a way of classifying compute nodes, the partition. Hopefully this answers the question. And the set of all partitions, it's basically forms the supercomputer. And the sinfo command shows actually exactly the partitions of a supercomputer. I've run this sinfo command on Zeus, and what the output is the following. We have a row. We have several rows with several information. The first column shows the partition. Well, each row actually represents a set of nodes that are in a particular partition and that are in a particular state. For instance, the first row tells us that some nodes in the work queue partition are available, and they are in the mixed state. It means that each compute node in that partition is partially used. There are some free resources and other resources are allocated. Instead, the second row tells us that other nodes, actually 26 nodes in the work queue partition, are allocated. It means that those nodes are fully booked. No other job can run on those nodes at the moment. The third row tells us that the 36 nodes in the work queue partition are idle, means that they are not utilized and they can accept jobs. And we have this kind of classification for each partition. So this gives you a view on the status of the supercomputer. I typically use this command to see, okay, there are nodes available for me to run my job at the moment, or how long, or what are the characteristics of each partition. For instance, we have that you can see that for the work queue, you have a time limit of 1 day. The time limit is the maximum amount of time your program can run for. And the long queue, for instance, is a good example of how partitions are used to distinguish between among nodes with different characteristics. We have a long queue, and it's called that way because it allows up to 4 days of execution time. The high memory queue has a higher amount of memory available, which is not shown in the default output of sinfo, but you can customize the output with several options. So you can see the CPUs, the number of CPUs available on each node, the number of nodes in the partition, and also the various host name of each node in the partition itself. So basically use this command to see what partitions are on the supercomputer, how many nodes are there, how many cores, and what is the time limit. As I said, for each partition is created because we have nodes with some characteristics that we want to group together. And each partition has a reason to be used. The work queue usually is used for the production jobs, the jobs that you want to run for several hours. You may want to develop or test some codes, then you can use the debug queue partition, which has a smaller time limit, but allows for a fast turnover, and etc. We have several queues with several requirements, with several characteristics. As I said, jobs are not executed instantly, but are put in a queue. So for instance, you submitted a job in the work queue, and you want to check how many jobs are waiting together with me. Well, at the moment, you can query the list of all the jobs in the queue using the sq command. The sq command will show you, and here is the output, will show you the list of jobs that are queued in a particular queue. So you can have a sense of how many people are waiting together with you, how many jobs are waiting to be run, essentially. And in particular, SQ will show both the jobs that are waiting, that are the state is PD, so pending, or jobs that are currently running. So the first three jobs in the output shown here are running, and the others are waiting. So for several reasons, some other jobs are waiting because there are not enough resources. Other jobs are waiting because they have not enough priority. Other jobs have a larger priority or a higher priority. So SQ command is useful to see what's the status of the queue, how many jobs are there, and how much you're likely to wait. And SLAR will also provide you with an estimate start time. So you have a start time or an end time. You can see that for the fifth job, for instance, it says that your job will likely start tomorrow at a certain time, but these are just rough estimates. It can change. You can filter the output of SQ. Oh, Pascal, some comments as well.
It's just to mention that the current systems at Pawsey, if you type SQ, you can kind of see the entire queue. But going forward, there'll be filters so that you can never know what the queue is like in its entirety, except for your group. Because and there are other clusters as well that are moving towards kind of not being able to see how everybody else's jobs are running. Because if you are not part of the group or not part of the, like in collaboration with that particular user, whether you should have a global perspective of the supercomputer is an open question. There's also privacy as well, like what jobs could be running. So if somehow you guys going forward eventually manage to get on Photonics, SQ will behave differently. You will not be able to see everybody just typing SQ and looking at all the jobs that are running or in the queue. You'll see essentially either your jobs or the group's jobs, and that's it.
Yes, that is a good observation, but still SQ will be useful because provides you tells you whether your job is running or not, or provides you an estimate of when it's going to run and why it's not running at the moment. Here we have several fields. We have the job ID. Each job is given a unique ID. You can use to query information about the job, the user who submitted the job, the group or account, the partition, etc. I hope you can try these commands as we go along. I think should be fairly easy. If someone has a problem executing these commands, please write in the chat. In fact, we have another exercise, and I can give you a couple of minutes to practice with the command. Yeah. So in the meantime, well, I can show you the commands that we have so far. We have done so far. Sinfo, for instance, this is on Zeus, and we have this configuration. And now, if I log out and I go on Topaz, I have my own SSH configuration, so that I don't need to type the password. And now I go on Topaz, and I again type sinfo. I see a different output, because now I am on another supercomputer, and so I see different partitions. I didn't need to go to log out and log in again, because there is the option -n, through which you can specify the cluster you're interested in. So for now, that I'm on Topaz and I type this command, Zeus, I see the status of Zeus from Topaz, and we can compare. So we can see that there are some partitions that are not available there are some partitions on Topaz that are not available on Zeus. For instance, the GPU queue. This is because Topaz has GPUs, whereas Zeus doesn't. The NVLink partition is for a special type of GPUs with a special interconnect. But the point here is that we have several partitions on several supercomputers, because these supercomputers different in the usage and use cases that they support. Now I try the SQ command on Topaz, and I see that there are a lot of jobs submitted to the GPU queue. Well, it's the main queue used on this supercomputer. But we have also another partition, which is called acceptance. Apparently, our admin are running some tests on the supercomputer. So you can see there are a lot of jobs running, but also a lot of jobs waiting to be run. And there is and you can see why they're not running by looking at the column that is called reason. The reason they're not running is because maybe the request node is not available, or there is a dependency that is another job has to complete its execution before this one can start, etc. Sometimes you just want to look at your jobs, because you want to look at the status of your jobs and you're not interested in the others. And then what you can type is sq --me, which shows you, and it will show you the jobs, your jobs in the queue. Currently, I don't have any job in the queue, so I see no output. Okay. So sometimes you can see that with sinfo, sometimes you will see that some nodes are down or drained. These are particular states that basically indicate that the nodes are not available for several reasons. Sometimes you can see that one node is reserved, and this is reserved because we are currently having a training, and we took that node and we reserve for this training. No one else can use it except us. Okay, we can move forward if there are no questions. The next topic is the allocation. So how you get access on the supercomputer in terms of, oh, sorry, my video is not, okay, my video is on. The next topic is about project allocations. That is how much compute capacity you're given on the supercomputer. So the supercomputer has a huge compute capacity, but it's still finite. And it needs to be partitioned across users in a fair way. The first step is to define a measure for the compute capacity, and supercomputing centers came up with the definition of service unit. So a service unit is usually defined at a very basic level. It's usually defined as 1 hour use of one core or one CPU core. If you have accelerators like GPUs, then you can define have additional definitions such as 1 hour use of one GPU is equivalent to 36 service units. But the point here is that once you have this definition in place, then you can quantify the amount of compute capacity available throughout the year on a supercomputer. And the unit of measure is the service units. So as a rough estimate, you can think of as the total number of CPU cores on the supercomputers multiplied by the total number of hours in a year, and that gives you the capacity of the supercomputer in service unit. Then what we do, we need to partition the quantity across researchers every year. That is, each research group gets an allocation of those service units, a portion of the total compute capacity. The way we do so is through a merit allocation process. Each year, a user or research group applies for time on the supercomputer and gets a certain amount of service units. At Pawsey, we partition furthermore each allocation in 4 parts that are equal in size, and that corresponds to the 4 quarters of the year. You need to consume each quarterly allocation within the quarter, otherwise it's gone. This is to incentivize user to say spread the use of the supercomputers across the entire year, and not to use the supercomputers only at the end of the year when they remember or have an allocation to use. This is because otherwise the system would be too congested to be used. Also, the amount of service unit you have available, or the amount of allocation you have used influences the job priority. That is how much time your job waits in the queue. And it's, for instance, if you have only used a small fraction of your allocation, then the scheduler will more likely give you a higher priority than other jobs of projects that have already consumed a huge part of their allocation. We also favor large jobs, that is, jobs using many cores, because that's the best use of a supercomputer running programs that cannot be run on normal computers. You can check, once you have an allocation, you can check the balance, so that is the amount of service units you have left, with the Pawsey account balance tool. And here it is shown an example. An example is shown about how to check the amount of service units that are consumed for the Pawsey 001 project. So there is a question about service units, right? You told me. So good.
John, I mean, I remember seeing Alexis commented that you can unmute. Do you have a question you want to ask?
I was actually, I think Danny put a question in the chat as well about the priority column in when you did like sinfo or one of the other, sorry, I forgot which command it was, but.
Yeah, so the sinfo, if you look at the priority number, the number itself is it's only useful in terms of relative. So it just tells you relative what your priority is relative to other jobs in the queue. So if you saw a number of 6,000, it in itself is informative. It's the priority relative to other priorities by Slurm, and the priority is dynamic. So it will increase as time goes on, but also if you had a low priority, but suddenly there's a really easy slot to fit in that job, and it's short, it might fit it in. So the priorities are indications. Higher priorities are more likely to be scheduled in lower priority jobs, but obviously it also depends what Tetris you can do with the job's resource requests, right?
Okay.
So higher priorities indicate that it's more likely to be scheduled, but there's no value at which you suddenly go, I know I'm going to be the next job running. The priorities kind of give you, and the start time, give you an indication of when you expect to start and what priority you have. But that's essentially it. And they're not consistent across clusters, right? Like the priority values are varied between clusters. So if you look at it,
yeah, one thing I want to add is that you actually can have a breakdown of that priority value.
Yeah.
That is the command as prio, or here the auto completion helps me. That gives you a, if we open the month page, it tells you that view the factors that comprise a job scheduling priority. So you can see the various reasons why your job has that priority. So I'm not sure I can see the priority of other jobs. Probably I can. You can give it a try. For instance, we have, if you go in the queue.
Can you increase the size of your window?
Oh yeah, you're right. And maybe decrease the size of the fonts. So for instance, let's just take this job. And then I do as prior dash J, that stands for, for the job. Unable to find jobs, probably because I cannot, it's not my job, so I cannot of course pick into the other job, but essentially this will output breakdown of the various components that make up your priority. But I don't have a quick example to show because I don't have any jobs running at the moment.
Yeah, okay, that's cool. If you don't mind, I was also going to ask if you could repeat what the up and down in underneath available meant.
So up means that the node is up, means that it's working.
Okay.
Means that it's functional.
Yeah.
Sometimes it's
like the
it's complicated. So it means that it's available. It means that it's actually in the partition, like it's available to be used, the partition. But then we have, as a partition, then we have you can have at the compute node level, you may have several states there. So the total partition, for example, the GPU queue is up in general, so it's available. But then you have one node that is down because some reason, maybe there's been some maintenance or something. One node is reserved, but then you have other nodes that are mixed or are allocated, which means that they're currently used by users. So the whole partition in general is up. You can use the GPU partition, but your job will likely be allocated, will be scheduled on the one of the 5 mixed nodes at the moment, if enough resources are available.
Okay. Yeah,
instead the other, the NVLink queue partition instead is done, means that all the nodes are not available, so the entire partition is actually down. Hope that answered the question.
Yeah, it did.
The second part is submitting jobs. So how do you actually run a program on the supercomputer? So as I said, a job is your program together with the requirements for it to run. And the main way is writing a script that specifies the way you want to run your program, but also the resources required. For example, number of CPU cores, amount of memory, which partition to use, and etc. Once you have that script, I'll show you in a second how to write it. You submit it to the scheduler with the sbatch command listed here. SQ, we have seen the command, and scancel is actually will tell you, will tells the scheduler, will tell the scheduler to actually not execute the job anymore, and if it's executing, cancel it. These are the main commands to interact with jobs. As I said, once you submit the job, you have an unique identifier for the job so that you can query information about the job. The script, you specify a job using a script, which is a bash script typically, or a CS script. But we advise using bash. And essentially, it's made up of two parts. The first part that are bash comments. They specify. Let's see if I have an example. Yes, here we specify the resources. So these are bash comments. So bash won't interpret them, but Slarm will. And in particular, through the syntax, you can specify several properties, such as the job name, which gives a job, which gives a name to the job, and it's easier then to find the job in the SQ output, for instance. Then you can specify the account, so which account will be billed for this run. So each account has an associated service unit amount available, and that account will be billed for the job. Then the most common properties are also the number of nodes requested, the number of tasks to run per node, that is the number of processes to spawn per node, and the CPU, the physical CPU cores assigned to each task, and etc. So this is the syntax to specify the resources, and then you can write your script. This is an example, and you can proceed writing your script in a way that then executes your program. This is a very simple example, and we are going to just execute the hostname command for here 20 times. Each 15 seconds, we execute the hostname command for 15 seconds. You can see that each script needs to start with the shebang line, that is specify which shell is going to interpret the script. Then you have the comments with the requirements. Each comment needs to start with the sbatch keyword, followed by the options. You can check the options are available for the sbatch command using the man page of sbatch, but these are the typical ones. So in this example, we are running a single process on one node, and the execution time, the time limit is 5 minutes. We are going to also use the reservation we have in turns queue, so that the job will be assigned to a node in the reservation. I'm going to explain reservations in a few seconds. But this is it. This is our first examples, and let's see if we have. Oh, we have the exercise. But first, the nodes on the reservation. So we have spoken about partitions. That is a way of grouping nodes, but we have also reservations. A reservation is essentially taking those nodes and reserve those nodes for a particular purpose and for a particular set of users. On the other hand, partitions are available to all users of the supercomputer, so you don't know who's going to get the access on the partition at which time. On the reservation, you actually know the users that are allowed to run on the nodes in the reservation. Usually, in our case, we have a reservation called interns queue, and just the people in the interns queue group, that the people that are in this training, can use the nodes in the reservation. So it's kind of a partition, but it looks like a partition, but its access is restricted to a certain set of users. And we can specify the reservation using the reservation -- reservation option. Okay, finally, each job has an associated output, that is the standard output, the standard error outputs that you normally have on your computer as well. The output will be written and redirected to the file, to a single file by default that is called slarm dash and the job ID. And that this collects the output from all the processes. So as I said, you can run a parallel program, so different processes, and the output of each one of these processes will be redirected to this output file. This is the first exercise that we actually, where we are actually going to submit a job to the scheduler, and the exercise is present in the repository we have downloaded earlier in the intermediate supercomputing or introductory supercomputing actually. I'll go on Zeus. So what it asks you is to essentially run a script present in the folder which is called hostname.slarm and see what happens. So it's basically practicing how to use the sbatch command. You already have the script there. You just need to submit it to the scheduler. Then you can check the status of the job using SQ, and then you can finally you can check the output by printing the content of the output file. So I'll try to do this exercise together with you. Okay, so introductory supercomputing, hostname, and we have two files. You should use the actually hostname.slarm. The other file refers to another scheduler that we don't have anymore, so we probably should delete it from the repository at this point. But anyway, so let's take a look at the hostname.slarm. And we can see there is actually something to be modified in this script. The reservation for today's course is not called Q, but it's actually called interns Q. So if I leave it that way, course Q, and try to submit this job, what happens is, let's see what happens. If I use as batch, it
course is another entry.
Yes, and that says the its job submission failed, and the reason is requested reservation is invalid. It means that does not exist. This is because the reservation for today is named interns queue. Okay, so if I modify this and try again, access denied to the reservation. This happens because my account is not in the reservation. So the reservation now is valid, but I cannot submit the job within the reservation. But you should be able to. So how can I solve this issue? Well, I can still submit jobs because I'm a user on the supercomputer, but I cannot do so through the reservation. I cannot use the reserved nodes, but there are still other nodes available. So what I can do is just say, I don't want to use any reservation. I might be waiting a bit more, but that's okay. So reservation, and to do so, I just leave the reservation field blank. So what I'm doing now is instead of specifying the option reservation within the script, I can override the content of the script by passing the same option to the sbatch command. In this way, this option has a higher priority than the one in the script. Okay, and so now it says submit a batch job and ID. Now the submission succeeded. If I do SQ me, it says that it's running. This is because it's a rather simple job, and there was a node available. I just requested one core, one node, so it was available, and my job is running straight away. If I check the output in the folder, I can see that if I check the folder, I can see that there is already an output file and with some output. And we have the date, the timestamp, because we call the date command in the script, and then we print the host name. So since you are running on a single node, the host name will be always the same. But what happens now, you can try to, again, to submit the same job. And again, I override the nodes option. Instead of requesting one node, I request two nodes. Now at this point, I have another job with another ID, and then another output. And in this case, I should see something different. It's the same host name. Q me. So this one has two nodes available. It's running. Task per node. Needs to check again the output. Interesting. I would expect to have different host names. So, well, let's see the reason why. Maybe that the other is still sending the output to the file. So I'm not sure yet, but how is it going to you? Have you managed to submit the reservation? Is there any question I can answer in the meantime? Oh, I see that. I know the reason. The reason is that I need to run this command. Yeah, now I need to run the command on multiple nodes. And to enable parallel computing, I need to use srun. So what I'm saying now is that I'm launching the hostname command on two nodes. So on two nodes here, and tasks, basically repeating what I have above per node one. It's just some experiments. I can set the other jobs in the queue. And now I delete the output of these ones. So this is just to show you some stuff, but it's quite advanced and will be shown later. Oh, okay. Clearly, I need to again submit this. Okay. And now I can see two host names. So I have enabled parallel computing on two nodes. I will explore these options, or Pascal maybe will explore these options later. But try not to waste too much time now. There are other commands you can use, but the SRAM provides. As control show job will show you some information about the job. The more you use the supercomputer, the more this will make sense to you. But it's a way of showing some properties of the job. We have tried the SQ and scancel together. I guess I'll give you 1 minute to try these commands as well. Then what we have, you may have some outputs, some errors, and these errors will be shown in the output file. Some common errors may be segmentation fault, because that is usually due to invalid memory access or not enough memory assigned to the job. Common error is the time eating the time limit. If your program runs for more than usually 24 hours or the time limit you impose, the programs will be killed, and you will see this error, no job canceled due to time limit. This is very important to know, because your program needs to be able to save progress and start again from the last save checkpoint. This is one of the things to know about the supercomputer and how to use it, and how it differs from using your laptop. You have a time limit. This is to give a fair treatment to every user, not to monopolize the supercomputer for too long by user. Other exercises explore the various combinations that I actually shown you, passing the options through the command line. You can specify different partitions. As you can see with the wrong reservation, I got an error. Not being part of a reservation, I got another error, and etc. So if you have questions or doubts, I can answer those. But essentially, yes. The final command, a very important command, that is saccount. Once your job has completed, you don't see it anymore in the queue because it's completed, but you can still retrieve information about it using the saccount command. With saccount, you basically access the database of all the jobs that you have executed or are executing. And you can display similar information to those you can see in other commands. For instance, job name, how many CPUs were allocated, how it ended, which code are completed, failed, out of memory, etc. We have, I know this is a lot to take, but we have a good documentation. There are links posted in the slides, but you can also find on Google. There's Pawsey Supercomputing documentation that will go through each of these information step by step and more in depth.